So ladies and gentlemen, I think we can get started. Thank you so much for joining us. We have a small group here. My name is Armagan Al-Haq. I'm the Manager of Program Development Partnerships and Finance at the Waterloo Institute for Sustainable Energy. And it's an honor for me today to introduce our guest speaker, Professor Ofelia Jianu, if I'm pronouncing the name correctly. She's an assistant prof of mechanical engineering at the University of Windsor in the Department of Mechanical, Automotive, and Materials Engineering. Her area of expertise involves energy systems, specifically multi-phase chemically reacting flows, hydrogen production, and the thermochemical copper-chlorine cycle for water splitting. She has published over 20 journal and conference papers involving particle dynamics, dissolution, and transport processes for hydrogen production. She is the recipient of the Canadian Foundation for Innovation John R. Evans Leaders Fund. Prior to joining the University of Windsor, Dr. Jianu was a project manager of the ORFRE Phase 2 project at the University of Ontario Institute of Technology. Dr. Jianu and her team continue to investigate phase transitions and transport phenomena with the goal of identifying local irreversibilities which are detrimental to the performance of sustainable energy systems. Dr. Jianu's research benefits Canada's efforts in reducing greenhouse gas emissions and support economic growth of clean technology, leading to the creation of new jobs, economic incentives for new investment, and commercialization opportunities in the clean energy sector. So ladies and gentlemen, please put your hands together for Dr. Ofelia Jianu. Thank you.
Thank you very much. Excellent introduction. Thank you. I hope the presentation is going to live up to that. Hi, everybody. So I'm Dr. Ofelia Jianu from University of Windsor. You've heard the introduction. I do study sustainable energy systems, and I look from the perspective of irreversibilities, where I apply the exergy analysis to minimize irreversibilities. Today, however, I will be talking about the hydrogen as a sustainable fuel and its role globally and in Ontario. So the motivation for today is to address concerns related to conversion of energy as one of well, energy is used everywhere, so converting it is pretty much making the environment a lot less sustainable. So we want to investigate systems that alleviate these environmental concerns and create clean solutions for local and global energy needs. So a little bit of trivia. Does anybody know what is the population of Canada and the population of Ontario? Yeah?
It's like
35 million. Anybody else? So for Canada, I'm guessing, not Ontario. Okay. And Ontario?
Probably close to 37 million to my knowledge, but
Yeah.
in Ontario, I can take a wild guess.
Yeah.
12 to 14 million?
12 to 14. So I have the data from 2017. I didn't check how much it increased, but in Canada, in 2017, it was 37 million, so very almost 37 million, and it's going up about 2 million per year. So we might be right there in 2019. And if we go down in Ontario, we are at about 14, and it's going up by about 1 million per year. So Ontario is the biggest like the most populated province. So why am I asking you this? Because I would like to know how many cars are being registered in Canada. Wild guess, if there are about 37, going by the 2017 numbers. And I said vehicles, so it can be anything from cars. Wild guess.
20 million.
20 million. Anybody else?
Just say any number.
Yeah. So from the Ministry of Transportation, there are, in total in 2017, 34 million vehicles registered. Out of these, we have the road vehicles at 24 0.5 million, and the rest are down the list. So
Type of vehicles or just light-duty vehicles?
So they are split. So this is total and road motor vehicles. So the light duty is about 24 million. And then we have vehicles weighing less than 4,500. And we also have the off-road construction farm vehicles that are about 2,200,000.
All types of transportation.
That's right. So pretty much anything that's using gasoline. So how about Ontario, now that we know where Canada stands? 14 million? Close. So we had a population of about 14 million, and there are total registered vehicles at 12 million. So that is, it almost looks like every person has a vehicle. Although some of them are off-road construction or trailers, a lot of trailers in Ontario. We do like to enjoy our outdoors, so so the breakdown is there. Why am I asking this? Well, because we're going to see that all these vehicles operate on gasoline. And gasoline, when it's broken down, when it's combusted into the internal combustion engine, you're taking gasoline plus oxygen, and you're going to output 8 molecules of CO2 and 8 molecules of water. So pretty much 99% of the carbon in the gasoline will be output as in the form of CO2. And we know it's a greenhouse gas. So the average vehicle outputs about 4.6 metric tons per year of CO2. Now, if we take it to Canada per year, we output about 158 metric megatons of CO2. In Ontario, 56.6 metric megatons, and the world is at 5.5 metric gigatons per year. So that is a lot of CO2 that we put out there by just operating our vehicles. I'm not talking about the extraction of the gasoline and refining and all that. So switching to hydrogen as a fuel, we combust hydrogen, burn it in the presence of oxygen, and the output is H2O. So it sounds great. Why not do this instead? So I'm going to talk a little bit about what's preventing us from just using hydrogen as a fuel. So a little bit about hydrogen. It is the lightest element on the periodic table. It exists in molecular forms attached to something. It doesn't exist on its own. So that's what makes it very hard to harvest. So we need to produce it from different, to break the bonds from other molecular forms. It's highly flammable in air at a wide range of concentrations and different temperatures, and it has a very high enthalpy of combustion compared to its size. So that means that it's going to give off a lot of energy. So the problem is that it doesn't exist as, come on in, you're welcome. It doesn't exist on its own. So we need to produce it. So where do we use hydrogen nowadays? This is, I think, from 2010, so the hydrogen use, not much has changed in the past 9 years. A little bit in the fuel cells, a little bit for lab analysis, so University of Waterloo, University of Windsor, University of Toronto, Victoria, we all do a little bit of research. We use hydrogen to polish glass, heat treatment, a little bit in food, so margarine uses hydrogen to hydrogenate it. basic chemicals. So that's for ammonia production. We use hydrogen. And refining of clean fuels. So that means we're refining fossil fuels. So we extract them from the ground, we deplete our resources, and then we use hydrogen to clean them. So that's how much hydrogen is being used per hour. So 100,000 per hour just for refining the fuels to make them cleaner so they don't output as much CO2. However, the present hydrogen production method, reformation of fossil fuels. So we take the hydrogen from fossil fuels, we use the hydrogen to clean the fossil fuels, and then we burn those fossil fuels in our engine, and we output CO2. So we output CO2 at every step of the way, not only in the utilization, in the burning of the oil, but in the production of the hydrogen that cleans that gasoline. About 3%, 4% is electrolysis. I think the numbers went a little bit up. Hydrogenics is our lead hydrogen production, located in Mississauga. They have a lot of research going on. I was at a conference a couple weeks ago at QTRIC, and I saw their power plant in collaboration with Enwave, where they have the fuel cell. It's about this big, and it produces hydrogen whenever we have surplus of electricity. Problem is, they are storing the hydrogen, and when they have surplus of hydrogen, they're going to release it. So we need to use this hydrogen instead of releasing it. So luckily, we have QTRIC, who's looking at transportation using hydrogen, and there are a lot of initiatives in this aspect. So I'm going to go a little bit through the hydrogen production processes, the fossil fuel and the non-fossil fuel. So fossil fuel, I'm going to discuss the steam reforming of natural gas. I'm not going to go into a lot of detail on it, and I should mention that my research team is doing a research for a literature review for the current methods of hydrogen production, and this is their work. I generate the ideas, my research team take it to the next level, so I have to acknowledge them. So steam methane reforming, what's happening, we're taking the methane and we reform it with water at very high temperatures and pressure, so that means it needs a lot of energy. The energy again comes from fossil fuels most of the times, so at every step of the way we are dependent on fossil fuels. So this is how much energy is being used. The next step is to take the carbon monoxide that's being released and again react it with water, and we're going to produce the CO2 and hydrogen. And then another option is to go to use this reaction back and forth, so it can be controlled. Problem with this steam methane reforming is that the output is a syngas, so it needs to be purified. Hydrogen doesn't come out in its purest form, and the purity of hydrogen is about 99.9%, which is not good enough for fuel cells. So it needs to be cleaned further before it can be used in fuel cells. The filtering techniques of the syngas, again, very highly energy intensive, pressure swing absorption, and in which you isolate the hydrogen molecule or the CO2 and then condensate the water. And you can also use a membrane to filter out the hydrogen. The second one is partial oxidation of oil. So in this one, you take the natural gas or liquid fuel, you oxidize it, you partially oxidize it, and it goes to, as a syngas, to the Swift reactor, where you're going to produce CO2 and hydrogen. And then it has to go again to the hydrogen purification reactor, where when hydrogen comes out in its purest form, you compress it and store it. The ratio of CO2 emissions to hydrogen generation is 3:1, and hydrogen purity is 99.99%. Still not good enough for fuel cells, because fuel cells need a purity of 99.999. So we need to do a little bit better than that. It is perceived as being able to produce hydrogen quicker than steam methane reforming and for less space. Coal gasification, this one is more than double the emissions of SMR, so steam methane reforming. It's a very inefficient process. It has only 59% thermal efficiency, and the hydrogen is extracted from the unrefined product. Again, it goes through a very long process in which very energy intensive reactions to purify the hydrogen, and so it can be used. Petroleum coke reforming, this one is very important in the Canadian context because of our oil sands. So in this one, we're going to take the pet coke and we're going to reform it to produce the hydrogen using these formulas. You need very high temperature of about 1300 Kelvin to be able to reform the hydrogen from there. So these are the fossil fuel methods that are currently used, and in Canada as well. So we use that method. Now we have the non-fossil fuels for hydrogen production, and you can use wind, you can use solar, you can use nuclear, you can use hydro. So I'll be talking a little bit about that. So water electrolysis, 99.99 purity. You pretty much take 2 electrodes, put them in the water, and you can break the bond between the hydrogen and water. It's a very mature process. It's been used a lot in, so it's very researched. It's advanced. The only thing you need is electricity and heat, and the water input, and output we have hydrogen and oxygen. There's a lot of research going on. So when the hydrogen was produced using water electrolysis in the past, it was very unsafe because the hydrogen and oxygen were being produced pretty much in the same container. So when they come in contact, there's a risk, a safety risk associated with that. However, through research, it got a lot better. What I'm going to be focusing on is the thermochemical water decomposition. Perhaps I should mention that the water electrolysis, because it takes electricity, can take electricity from either wind, solar, hydro to make it clean. The moment you take electricity from a power plant that uses coal, it's not a clean method anymore. So hydrogen is only as clean as the method used to produce it. So we have to be mindful of the environment as well. Now the thermochemical water decomposition, there are advantages and some disadvantages to it. So advantages are that it produces the hydrogen and oxygen in different reactors. So they are spaced, and the risk of hydrogen and oxygen coming in contact is minimum, so it's very safe. The purity is 99.999%, so it can be used in the fuel cells. And the chemicals that you use in a thermochemical cycle are recycled internally, so you never release any emissions. The disadvantages, there isn't enough research done on them, so they're still quite expensive. So far, low efficiency, and we'll talk about what we can do to increase the efficiency. And they also have very high temperature requirements. So to date, the only thermochemical water decomposition cycle that is implemented is, so it's being used to produce hydrogen, is in Japan, the sulfur iodine thermochemical cycle. And the chemicals that you put in the reactors most of the times are highly corrosive, and the reactors cannot withstand those kind of harsh environments. So what they used in Japan in the sulfur iodine, they used gold to make the reactors. So that's what's going to drive the price very high. So it's going to be a very expensive method to produce the hydrogen. However, it produces it at very high amounts. You can have a plant that it can be scaled up. So that's the advantage of it. What I'm working on, and my research team, what we're working on is the copper chlorine cycle for hydrogen production. And this cycle, there is a lab scale cycle at the University of Ontario Institute of Technology. That's where I was a project manager for this project. And the advantage of this cycle is, well, it has three reactions. Some argue that it can count as 4, but you put in the water and heat. You produce at 400 degrees Celsius. You have a hydrolysis reaction where you're going to be producing a double salt, and we call it copper oxychloride. So this is going to be a solid when it comes out. It doesn't exist in nature. It's being produced in that reactor. The challenge is to move this double salt. So the salt goes from being produced at 400 degrees. It has to be moved to the next reactor, which this is a little bit out of date. After a lot of experiments, we determined that this reaction happens at 450 degrees, so a little bit lower than we thought. When the copper oxychloride melts at 450 degrees, the oxygen is going to break off from the double salt. It's going to be released outside of the oxygen reactor, so we're going to be collecting it. And the copper molecule is going to attach to the cupric chloride to form CuCl, cuprous chloride. And that is going to be in molten state. So in this reactor, you have a 3-phase reaction. You have the solid coming in as copper oxychloride. You have the molten CuCl, and you have the oxygen gas going to the surface and escaping. Some research that my research team has done is to do some simulations of mass transfer into gas bubbles to see how much mass is going to be transferred to the surface, because when oxygen is going to carry out some of the cuprous chloride, it can clog. The cuprous chloride is going to solidify instantly once it goes below 400 and about 25 degrees. So if it enters the exhaust of the reactor where the oxygen is supposed to escape, and if there is CuCl attached to it that enter the bubble, then the exhaust is going to be clogged, and that's a safety concern. So that's some research that is still ongoing. We haven't actually tested it with the actual chemicals. We did the experiments with different chemicals that are not as harsh and not at such high temperatures. Once the CuCl comes out in the liquid form, we extract the heat, and it becomes solid. And so in between these two reactors, you're going to have a dissolution cell where the CuCl will dissolve in hydrochloric acid that's coming from the hydrolysis reactor. So we have hydrochloric acid coming out as gas, but we'll make a solution of hydrochloric acid. So, and combine the two CuCl and hydrochloric acid to send it to the electrolyzer, in which at 90 degrees we have hydrogen being split from hydrochloric acid rather than from water. It's a weaker bond, so it's less energy intensive. So to break the bond of water in, the bond of hydrogen and oxygen in water, you need about 1.23 volts, whereas to break the bond from hydrochloric acid, we were successful at breaking it with 0.76 volts, so a significant reduction. So hydrogen is being collected. This reaction happens at about 90 degrees Celsius. There are some experiments done at the Canadian nuclear labs as well. They are highly active on the electrolyzer. They found out that the electrolyzer is the most efficient when it operates at about 80 degrees and 6 molar hydrochloric acid. Now, for here, we need to recover the heat when we output the CuCl, because this reactor operates at 450, whereas this one at 90 degrees, so we have a big temperature difference, and we can recover some heat. So my students designed a quench cell to look at pretty much how much steam is being generated when you quench the CuCl into water, and if there isn't much steam generated. Of course, it depends on how much CuCl you're quenching and how much water. So this one is done at lab scale, so we're quenching about 100 grams of CuCl. Now we're quenching about 100 grams of CuCl in about 1 liter of water. So we're starting small. Now, of course, because the CuCl comes out at such high temperature, it's above the heat of vaporization of water, so you will have flash boiling at the surface, but you can also have explosions in the water, and it can put a lot of impact on the sides. So we're starting with lower temperatures, not quite with CuCl, and we're observing what's happening to the salt when it's being quenched, to see how it's mixing with the water. CuCl doesn't dissolve in water, so it's going to settle at the bottom. So it's going to be, again, a multi-phase flow in this cell. So they are starting the experiments on July 5th. So some research has been done on quenching the CuCl. However, they used air. CuCl will oxidize in the presence of air, and it will change the form from CuCl to a different complex, and it's almost impossible to predict which complex it's going to be formed, because CuCl is also light dependent. So depending on what kind of light you have, it will change to a different complex. So we're going to be doing the experiments in the presence of nitrogen rather than air. It's an inert gas, and we're going to remove all the air from the cell to ensure this the CuCl stays in the form of CuCl. Another study, so pretty much the mixing of CuCl with water will be observed with shadow imager. So this shadow imager is going to tell us how does the CuCl behave in the water and then in the hydrochloric acid, because we would like the CuCl to start dissolving in the hydrochloric acid as soon as possible. So to remove the step of quenching in the water, if we could quench straight into hydrochloric acid. If a lot of vapor is being produced when we quench, then we may not be able to quench straight into the hydrochloric acid. Due to safety concerns, hydrochloric acid could enter the oxygen reactor, which could be hazardous. So that is on the thermochemical copper-chlorine cycle. A lot of research has been done, and a lot of research is still needed to get this cycle to be fully operational. There is a lot of research at University of Ontario Institute of Technology where they have the lab scale. I'm looking more at between reactors what's happening, whereas UIT is looking at what's happening in the reactor. So they are more concerned with how much hydrogen is being produced and how much oxygen is being produced. Whereas I'm investigating transporting the materials from one reactor to the next. So this is this work was done by my grad students. Another grad student is working on a different method to produce hydrogen and for a different purpose. And the reason I thought this was very interesting to discuss is because it's practical. It can be implemented. So Comber Wind Farm is somewhere between Windsor and London. I'm not sure how many of you traveled that stretch on the 401 and saw that sometimes the wind turbines are turned off even if there is wind, and sometimes they're operational. So one of my students really wanted to see why the wind turbines are being turned off. He didn't really believe me when I said that it's potentially because we have surplus energy. So he did his master. He's doing his master's, and he's now convinced. So so he started by looking at how much power is being produced by this wind turbines. So on the previous figure, so the blue points are the wind turbines, and the red is the station where the data is recorded, so the meteorological station, because we need the temperature and the pressure and the wind during that day. So all this data was recorded from that station, was obtained from that station, and he observed that at 12 a.m., between 12 a.m. and 3 a.m., very low power is being produced, and then power all of a sudden, more power is being produced with these wind turbines, and then about 7:30 is going down again, and then it's going up during the day. And then there's a small drop again between 3:30 and 5 o'clock. Again, we have a lot of power being produced by the wind turbines, and then after 10 o'clock, power goes down. And he thought that it's perhaps because there wasn't any wind. So he plotted the wind velocity to see if there was wind during those times or not, and see if the wind turbines were turned off due to no wind. There was a lot of wind. If we look at the previous slides, so here there was very nice wind, sufficient for producing a lot of power, but the wind turbines were turned off. So he came up with this idea that we could produce hydrogen with the curtailed power, and he wanted to see how much hydrogen we would produce. And if we produce this hydrogen, how about we help a northern community in Ontario, which northern communities in Ontario are highly dependent on diesel generators. So there are about 150,000 people living in northern Ontario who have diesel generators. Diesel is being transported to them because, so he pretty much thought that, well, if we produce the hydrogen here, we can transport a clean fuel and use hydrogen to power their northern community rather than use diesel to power the northern community. So he did some investigations of how much hydrogen can be produced and using the data. So he looked at the curtailed data from previous years up until 2017. So this is how much power could have been produced. His goal is to develop pretty much to project the values to see if there is a trend, and we can predict the amount of hydrogen that could be produced and we could transport to the northern communities. Now this northern community, so he chose the Sandy Lake northern community, and he looked at if we are using a fuel cell, this is a fuel cell from Hydrogenics, what is the efficiency, the exergy efficiency and energy efficiency of the fuel cell? So he plotted all of them for different current, just to see what's the best operation for the fuel cell. Now, he also did the exergy efficiency for a PV panel. So this is data from the Sandy Lake community. So they do have a lot of sun. So he was looking into when we cannot transport the hydrogen, can we power that community using sustainable resources rather than diesel. So it looks like the exergy efficiency is between 25 and 10%. So this is per year, so 365 days starting on January 1st. And he did 3 years. He did the same for the, he plotted the exergy efficiency as well for the different years, just to compare the PV with the hydrogen generation based on exergy grid here. And he also plotted the wind. So wind for 2013, 14, and 15, and solar. So it looks like he did it per month. So in the middle of the year, so you have the wind is not very good at the beginning of the year when it's colder outside and there isn't much wind at the Sandy Lake, but the solar is very good, colder conditions, so solar panels are more efficient. And then at the end of the year, same idea. In the middle of the year, both of them are similar efficiencies. So what he's planning to do is to provide a fuel blend for the Sandy Lake community to see when, and the predictor of when the PV can be turned on, the wind can be turned on, and when we can use hydrogen to make up for whatever losses. So in conclusion, hydrogen production, steam methane reforming, still #1 production method, but we need to move away from them, from steam methane reforming. We need more sustainable alternatives for hydrogen production. And one of the methods is the thermochemical cycle, or using fuel cell electrolyzers in collaboration with Hydrogenics and other companies as cleaner alternatives. But a lot of research is still needed. So thank you very much for your attention. If there are any questions, I'd be happy to entertain them.
So I came because I was interested in hydrogen for a long time, and what people have always talked to me about is the difficulty of storage and transportation. So I'm interested for the idea of using the wind farm and the power there. How would they get the hydrogen? How would they store it, and then how would they get it up to Sandy Lake?
So I'm not really looking into the storing and transportation, but I was talking to somebody from Hydrogenics, and they are producing the hydrogen that they are producing, they're storing it. There is a lot of research on storage, and there are ways. You can transport it, you can compress it, you can, there's like different ways to store it. So I don't know if you, if there's anybody has any ideas of that research. I don't look at storing the hydrogen and transporting. That would be another topic for another master's thesis, to look at how it's going to be transported there. But yeah, we usually release it when we produce it. Yeah, we don't produce that much.
We had a brief chat before the excellent presentation, but I want to go back to, I'm watching this for about 25 years. There used to be a group in Canada called CHES, Canadian Hydrogen Energy Society. It lasted for quite a while, but in the last 10 years it's sort of gone away. But I really think if somehow we could form a national group with hydrogen in it to coordinate all this, there's good work being done all over, but it has to be focused. And then we can get more funding from the governments at all three levels. So is there any way we could take an action or somehow reformat CHES to coordinate all this good information?
Well, I'd be happy to do something like that, and I know there are quite a few institutions who are looking at hydrogen, so it's something that we can discuss between the University of Windsor, University of Waterloo, and U of T. I know they're quite active into hydrogen production. University of Ontario Institute of Technology, I know Victoria and Ballard on the West Coast is also quite active. So potentially we could do something like that. There is a very, I know in US they're quite active on hydrogen as well, and they have the World Hydrogen Energy Conference that attracts over 2,000 people where they discuss hydrogen production methods and recent advances. So we can definitely look at that and then combine, because I think we should look globally how we can, staying just in Canada, I think starting in Canada, having a group like that and then going bigger would be beneficial. But thanks for the suggestion. That's something I'd be interested in.
Two more, so one. First, okay, sure.
Hi, I was just wondering, in the thermochemical cycle that you were talking about, you still had electrolysis at the bottom of that system, and the idea is just that it uses less energy than water electrolysis?
That's right. I'm just going to scroll.
Because you'd said earlier on that it was less efficient, so then I wasn't...
So the reason it's less efficient, so overall, the cycle is less efficient, whereas the electrolyzer uses less energy to split the hydrogen from hydrochloric acid. But the cycle overall is, the efficiency is about 32% right now. The one way to increase the efficiency, the overall efficiency, is to combine the thermochemical, the copper-chlorine cycle. Because of the temperature requirements under 500 degrees, it can be combined with nuclear power plants. The waste heat from nuclear power plants is at about 450 degrees. So if that energy can be used in one of the reactors and drive this reaction at 400 degrees Celsius with waste heat, and it's not only nuclear power plants, but cement plants they give off heat at 1200 degrees Celsius. So if that can be harvested and used to drive the reactions, then the overall thermal efficiency will go up.
That's the play. The play is to use waste heat.
That's right. That's right. Yeah, for this particular one, and the CuCl1 can work with that. The other thermochemical cycles operate at temperatures of above 1,000 degrees Celsius, so they need solar to operate. Otherwise, the efficiency goes very, very low. Yeah.
First of all, thank you for your presentation. How do you see the future of hydrogen in Ontario and Canada?
How I see it, well, I'm hoping the research continues. One of the reasons I'm hopeful that we will be successful is that QTRIC is very active in getting grants, and their goal is to, if I remember correctly, and I hope if they hear this presentation, they're not going to be after me, but they were saying they want, their goal is to switch all the transportation, the public transportation to hydrogen or electric, so to make it more like environmentally friendly. So they, I don't know by what year, but they want to switch it all. There are, I believe in Mississauga, 20 buses were purchased, hydrogen buses, so that's a start. If we start using the hydrogen, we need to figure out a way to produce the hydrogen and also the infrastructure. I believe that at least in Ontario with Cutric, and the West Coast is quite active as well, I think there is a need. Also, if we continue using fossil fuels for our cars, because I don't foresee that we're going to stop using it in one day. There's not going to be any fossil fuel-based internal combustion engines. If we continue doing that and we want to refine the oil with using hydrogen, we need to look at cleaner methods of hydrogen production. So even coupling with refineries to get their waste heat and produce hydrogen using either the thermochemical cycle or electrolysis wherever possible. So in my opinion, it's a matter of finding out what's the best method for the area where you're in. So in Ontario, we have refineries near Sarnia, 3 of them. We can tap into that market, but other provinces don't have refineries. They have a lot of water, so for them it would make sense to use water rather than fossil fuel based. Okay.
I just want to follow up. So what is the goal? Like, how much more efficient would this cycle be if you used all waste heat compared to water electrolysis?
I'm not sure. I would have to look into it. So I know that right now, because of the reactions and because of the thermal requirements, is at 32. But it would be a study I'm gonna do and maybe get back to you.
All right, and I was wondering, what is the difference between that electrolyzer and a water electrolyzer?
So this one, in this electrolyzer, we're using the, what is it called? It's not on my mind right now. So it's not, it's similar to a water electrolyzer. So proton membrane exchange, so PEM electrolyzer, that's what we're using here. So the problem with the electrolyzer right now is that the membrane gets clogged with copper. So there's a lot of studies done. CNL is very active in figuring out how to extend the life of the membrane and also make the electrolyzer more efficient.
I see there's a lot of complexity in the infrastructure to do these various extraction methods. The water electrolysis, is it a complex infrastructure that's needed, or is it fairly simple?
The water electrolyzer uses high temperatures, like higher temperatures, and a lot more like higher voltages to split the water. The electrolyzer, the one I saw at Hydrogenics, very small, they also use a PEM electrolyzer, so it can be used like that. So it's not, they are comparable, the electrolyzers. And the only thing is that, I guess, in this one you produce hydrogen at very high quantities of hydrogen. So a refinery would probably want something like this rather than an electrolyzer that has a harder, like it would take longer to produce the hydrogen. So depending on what is the hydrogen requirement, you would go with something that can produce a lot of hydrogen at once.
I guess what I'm wondering is the biggest downside to something like water electrolysis, is it the amount of electricity required? Is it the heat needed, or is it the extraction or danger of the extraction process?
The electrolyzer, so from what I know, they do need the electricity. So if we don't have the surplus electricity, it's a little bit hard to produce it, whereas this one can be coupled with a solar panel or the wind turbine. So still use the surplus electricity, but because it uses a lot, it has lower requirements. A solar panel would be can be attached directly instead of waiting for surplus electricity from ISO.
I guess what I always wondered was the idea of something like I sort of picture like a trickle charge, just continually over days and days, just gathering sunlight, breaking down water, turning it into hydrogen and storing it, and eventually, so if you had a lot of these things and distributed it, that you could be autonomously doing this if you had enough of it generating.
Yeah, and the electrolyzer, PEM electrolyzer, water electrolyzer is about 60% efficient. So they also have losses, but there is research and hopefully it's going to get better. Yeah.
Thank you. I want to introduce the concept of utility corridor, utilidor. Two things come to mind. We're trying to get transportation under control. So there's been moves for 25 or 30 years to take the rail tracks from Windsor all the way through to Montreal and have one for freight and one for passenger service. So when that comes, how could you combine that with, you look at along the 401, for example, two things come to mind. The gasoline stations, could we have hydrogen refueling stations put there, but also these warehouses, like it's going to need an upgrade to the electrical transmission system to coordinate to put all of these together so you have one utility corridor, sort of one big spine servicing all of these. It's a big ask, but if somehow the people working on these projects could get together to maximize, optimize these projects to feed each other, okay, it would save a lot of money, utility corridors.
Mm-hmm. There's definitely a lot of research into where to place the charging stations. Yeah. Right now, I mean, if we look at fueling stations for our cars, you pretty much have almost at every corner you have at least 3 different ones. So today I had a hard time deciding if I want to go to Esso or Petro-Canada or Costco. So to get hydrogen to have the same convenience, it's probably going to take some time because we're not quite there. Also, the demand, it's not as high yet, but it has to start somewhere. So once we start with this 20 buses, I believe they are being charged at the cement power plant in Mississauga, where Hydrogenics is producing the hydrogen with their electrolyzers.
Questions? Okay, so I promise you that our guest speaker will be here for the next 10-12 minutes if you would like to have a chat with her on a face-to-face basis, but then we have to go for lunch. So on behalf of University of Waterloo and Waterloo Institute for Sustainable Energy, I would like to thank you for your wonderful presentation and sharing some wonderful insights with us. So ladies and gentlemen, please, let's put our hands together and thank Professor Ofelia Jianu. Thank you so much.